So now let's talk about the critical value approach. Okay. Now before we talk about the decision rule, I just want to refresh your memory on a concept that we looked at when we studied confidence intervals. Okay. So let Z sub alpha be the Z value such that the area under the standard normal curve to the right of Z sub alpha is alpha. Okay. So if you draw a normal distribution, the standard normal, right, and suppose you have Z sub alpha, then this shaded area is going to be equal to alpha. Okay, and so given a value of alpha, you should be able to use the standard normal table to find what Z sub alpha is. Okay? And we have done this in the past. Now, again, we have lower tail tests. We have upper tail tests, and then we have two tail tests, right? Now for lower tail tests, the critical value is negative Z sub alpha, where alpha is the level of significance, right? And I should say CV stands for critical value. Right? For upper tail tests, the critical value is Z sub alpha. And then for two tail tests, we have two critical values. We have Z sub alpha over 2, and then we have negative Z sub alpha over 2. In other words, the two critical values are plus minus Z sub alpha over 2. Okay. Now, our decision rules are as follows. For lower tail tests, we reject the null if the test statistic is less than the critical value. In other words, if the test statistic is less than negative Z sub alpha. Now for an upper tail test, we reject the null if the test statistic is greater than the critical value. In other words, if the test statistic is greater than Z sub alpha. Okay. For two tail tests, the decision rule is we reject the null if one of the following two statements is true. First, if the test statistic is greater than the positive critical value, which is z sub alpha over 2, okay. Or if the test statistic is less than the negative critical value, which is negative z sub alpha over 2. Okay. Now, theoretically, we can test at any level of significance, right? We can test at 20% level of significance, we can test at 50% level of significance, and so on and so forth, okay? But in most real-world applications, there are 3 levels of significance that we pay particular attention to. They are the 10% level of significance, so alpha is 10% or 0.1. The 5% level of significance, so alpha of 0.05, and then the 1% level of significance. So alpha of 0.01. Okay. So I'm gonna have here lower tailed, upper tailed, and then two-tailed. So for a lower tail test, the critical value when alpha is 10% is going to be negative 1.28. When alpha is 5%, the critical value of a lower tail test is negative 1.645. And then when alpha is 1%, the critical value is negative 2.33. Okay. For upper tail tests, the numbers are 1.28, 1.645, and 2.33. And then for two-tailed tests, when alpha is 10%, the critical values are plus and minus 1.645. When alpha is 5%, the critical values are plus and minus 1.96. And then when alpha is 1%, the critical values are plus and minus 2.58. Okay? Now, there's one very important point that I need to mention. Okay. And it is that the discussion on decision rules so far, right, pertains to the case where the population standard deviation sigma is known. Right? How do I know that? Because if you look at the values that we've been looking at, we all use the standard normal, the z table, right? When we don't know the population standard deviation, so when sigma x is unknown, in principle, everything applies, right? Everything works except what? Except that we have to use the t distribution with the appropriate degrees of freedom, right? Okay. So this is a very important point that I want you to keep in mind. If you use these values, if you use the critical values I give you up here in this table for a problem where we know the population standard deviation, then you're fine. But if you use these values for a problem where we don't know the population standard deviation, then you may reach a wrong conclusion. Okay? So be very careful.